We now want to look at how pH affects solubility. Previously, we were looking at the common ion effect, and now we want to look at how the pH affects the solubility. Well, if our substance has a basic anion, then anytime we add something acidic, it's going to make that substance more soluble. And the example that I have here is lead fluoride versus lead iodide. For lead fluoride, it has some solubility. It's limited solubility. To the extent that lead fluoride dissolves, you get lead ions and fluoride ions. Well, if you put a strong acid in with that solution, then adding that strong acid is going to react with some of those fluoride ions, meaning that you're essentially removing them from solution. Now, they're still there in the form of HF, but it removes them for purposes of looking at the equilibrium constant. So we will find that by removing that it's like removing something that is a product. It will drive that equilibrium to the right. If we compare that to lead iodide, well, lead iodide, iodide is the conjugate base of Hi. That's a strong acid. So adding another strong acid to it is not going to react with the iodide. So the solubility of lead iodide is not affected by having a strong acid in solution. So that is kind of cool. Now, another thing is what if you have hydroxide ion, because some of the things on our equilibrium constant page, Appendix D3, which I'm going to come back over here. Here's Appendix D3. Some of these things are hydroxide. So like there's cadmium hydroxide, there's manganese hydroxide. There's a whole bunch of these. There's magnesium hydroxide. So we've got a whole bunch of those. And so one thing we can do is use a buffer solution. When we use buffer solutions, the cool thing is that there's no change in the concentration of hydroxide ion, meaning that in a buffer solution, when we do our concentration table, it's going to be a lot simpler. So I will show you how that works on number 54. So let's look at number 54. So here is number 54. Let me clear out our stuff from that previous section. So here's number 54. We've got the molar, we want to calculate the molar solubility of iron 2 hydroxide. So I'm going to go ahead by writing FeOH2 solid, and it dissociates to some extent to give us Fe2 plus AQ plus 2 hydroxide AQ. And we are going to have a concentration table directly beneath this, which I will show you here in a minute. But over here, let me write out the equilibrium constant expression for this. So KSP is going to be equal to the concentration of iron 2 times the concentration of hydroxide ion squared. And we're going to go over to Appendix D and find. So going over to Appendix D, and we are going to find the equilibrium constant for iron 2 hydroxide. It's right there, 7.9 times 10 to the negative 16. So 7.9 times 10 to the negative 16 is our quantity there. All right, well, so now we have some buffer solutions at 7, 10, and 12, and we want to see how these buffer solutions will affect the solubility. Again, for the solid, it doesn't go into the expression, so we're not going to worry about it. Iron, the original concentration of iron in that solution is 0. We're assuming there is no iron in that buffer solution. But the original concentration of our hydroxide ion is going to be not 0. Because the pH is at 7, so with a pH that's equal to 7.0, that means our pOH is equal to 7.0, because 14 minus 7 is 7, which means our hydroxide ion concentration is equal to 10 to the negative 7. Well, when we put that in here, this will be 10 to the negative 7. Normally, we wouldn't put such a small number into the concentration table because the change would completely overwhelm it. We wouldn't need to worry about it. But because this is a buffer solution, that concentration of hydroxide isn't going to change. So while this will be plus X, this will be no change. And so it will remain 10 to the negative 7. So now when we put that over here into our solution, we'll get our KSP is 7.9 times 10 to the negative 16, and that is equal to X times 10 to the negative 7 squared. Well, that means that X is 7.9 times 10 to the negative 16 over 10 to the negative 7 squared. And when we put that into our calculator, 7.9, I already know what this is going to come out to because it's a simple problem. But we're going to divide that by, so 1 times 10 to the negative 7 squared. And so we're going to get 7.9 times 10 to the negative 2 molar. And that is going to be our molar solubility. It's going to be our molar solubility in pH equal to pH equal to 7. I'm going to select a different color for this this particular one just to differentiate here. So we'll again do initial change equilibrium. Make sure that shows up on the camera. It's green. It looks kind of gray there, but it's green. All right, so iron is 0 plus X is X. Since the pH here is equal to 10.0, that means pOH is 4.0, which means that our concentration of hydroxide is 10 to the negative 4. Doesn't change because it's a buffer, and this will stay 10 to the negative 4. So now when we calculate this, we're going to get 7.9 times 10 to the negative 16 is equal to X 10 to the negative 4 squared. So X is 7.9 times 10 to the negative 16 over 10 to the negative 4 squared. And that's going to come out to 10 to the negative 8, but I want to show you so you believe me here. So 7.9 times 10 to the negative 16, and we're going to divide that by 1 times 10 to the negative 4 squared. And we'll get 10 to the negative 8. So 7.9 times 10 to the negative 8 molar. Okay, so now let's do this last one. Initial change equilibrium. Our initial concentration of iron is 0, so plus X is X. Since our pH is 12, hopefully you're able to follow along here. Since our pH is equal to 12.0, and that means our pOH is equal to 2.0. That means the concentration of hydroxide is 10 to the negative 2. It doesn't change because it's a buffer, and that'll be 10 to the negative 2. So now we can put that into our expression. And so we'll get 7.9 times 10 to the negative 16 is equal to X times 10 to the negative 2 squared. All right? So X is 7.9 times 10 to the negative 16 over 0.010, because that's 10 to the negative 2 squared. Okay, and so now we'll punch that number in. 10 to the negative 2 squared is going to be 10 to the negative 4. This will come out to 10 to the negative 12, but again, let's go ahead and punch that in. Negative 16, and we'll divide that by 1 times 10 to the negative 2 squared. And that gives us 7.9 times 10 to the negative 12 molar. And sorry it got all scrunched up here at the end. I clearly should edit this page and make this bigger. Okay, so we've now looked at how pH can affect the molar solubility. Our next section, now this particular section ends up not being on our learning objectives, but it is kind of interesting, so I do like to show it, and I also like to show how it connects to something that we do in the lab. So complex ions, so these are some equilibrium reactions, and notice all of these equilibrium reactions have very large values. Well, these are called formation constants. We'll find that if you put a metal ion, which is a Lewis acid, into a solution that has some Lewis bases, and those Lewis bases here are going to be things like usually like ammonia. Here's cyanide, there's thiocyanate, bromide. So it's things that have a lone pair of electrons. And another thing we call Lewis bases, we call them ligands. In later chapters that we don't get to cover in this class, it talks about ligands. So the formation of these complex ions will increase the solubility of these sparingly soluble salts. So these things that aren't normally very soluble, we can increase their solubility simply by using this. So the one that we're going to use is this, because in lab we do an experiment where we make a precipitate out of silver chloride. So we have silver ion, there's chloride ion, and it precipitates to give us silver chloride. But then in our next step, we take some ammonia and we dissolve that silver chloride. And then we dissolve that silver chloride just by adding a little bit of ammonia. And I want to show you why that works. So, and then here we can describe this using what's called a formation constant. So it's called a formation constant. And we used Kf as the designation for a formation constant. And as I mentioned, these are large numbers. These are significant numbers. So, okay. Now, this particular complex ion that is with silver, we call it hexaamine silver complex ion. If you're curious about the nomenclature for complex ions, feel free to go to your textbook and go to chapter 23, and there is a section in there talking about the nomenclature of these complex ions. Pretty fun stuff, but just before you look at that, you say, oh, you put too many letters in there, right? Trust me, that's the real thing there. So the dissociation of silver chloride, this is one that, like I said, we do in lab. Silver chloride is not very soluble. Here is our solubility product for silver chloride. And if we add that reaction to the formation constant one, so silver plus 2 ammonia molecules gives us the silver diamine complex ion. So it says hexa. It should be, oh my goodness, I made a mistake here. This should be the diamine, not the hexamine. Anyway, I forgive myself. So anyway, there is the complex ion, and there's 2 of them. So so that means that here we're going to have, when we add those 2 equations together, this will be our net equation. But then look here. When we add equations together, we multiply their equilibrium constants. So when we multiply these 2 equilibrium constants, we get 3.1 times 10 to the negative 3. Now, while that is still technically a reactant-favored reaction, we have quite a bit of control over this, because if you look, if we want to drive this reaction to the right, we can just add more ammonia. typically when we're doing this, we add 6 molar ammonia. So we can get quite a high concentration of ammonia when we do this. So here we've got the silver chloride that is precipitated. There is tiny amounts of silver and chloride ion in solution. The ammonia will react with the silver ion. So when that happens, more of the silver chloride will dissolve, and we can get pretty much all of it to dissolve because of the formation of these diamine silver complex, not hexaamine. I'm so embarrassed. I will fix that on the presentation. All right. And now we want to look at a concept that we call amphoterism. And ampho just means both, kind of like amphibians, or amphiprotic. Amphiprotic is something that's both acidic and basic. Amphoteric is something that will react with both an acid and a base. So amphoteric oxides and hydroxides are going to be insoluble in water, but they will be soluble in either strong acid or strong base. So they can act like an acid or a base. Now, some examples of things that act as that act as amphoteric substances are going to be oxides and hydroxides of aluminum, chromium, zinc, tin. There's a few others. Most often, you'll find these showing up near the middle of the periodic table. So we're going to look at silver, zinc, or not silver, aluminum, zinc, and tin, and I'll show you those are all near the middle of our periodic table. So there is aluminum in group 3, there's zinc, tin. I think maybe even cadmium does this, but I'd have to look that up. So chromium is over here. It acts a little bit differently, but there's that. I think lanthanum may do this as well, but I'd have to look that up. The point is, that those particular substances tend to react with both acid and base. So here is an example. Aluminum hydroxide is not soluble in water. So right here in the middle test tube, it is not soluble in water. But if you add H plus to it, the H plus will react with the hydroxide and we'll get aluminum ions, and so everything will dissolve. So we will have using a strong acid solution, we can get it all to dissolve. Conversely, if we add a strong base, by adding a strong base, we can form a complex ion of aluminum, which is soluble, and that will also increase its solubility. So soluble in strong acid, not soluble at a pH of 7, and then soluble in strong base, which is a pH much greater than 7. So pretty cool little trick. And like I said, aluminum does that, and I know zinc and tin. There's a couple of others, but these are just a couple of those examples. All right, so we are to section 17.6, and this is the next to last slide in the presentation. And I call this section "Will a Precipitate Form?" Will a precipitate form? And playing Will a Precipitate Form is a fun game, great game to play at parties in case you're hosting any parties anytime soon. You can put up a problem and say, will a precipitate form? And then if people get it right, they can maybe win door prizes or something like that. Okay, so let's look at this. If you have an equilibrium reaction, a solubility product constant and solubility product reaction, you can figure out a reaction quotient Q. Now, we talked about Q way back in chapter 15, and Q shows up again. So if Q is the same expression as K, but not necessarily at equilibrium. If Q is equal to K, that means our system is at equilibrium and the solution is saturated. If Q is less than K, that means, KSP, that means more solid will dissolve until Q is equal to KSP. And if Q is greater than KSP, then the salt will precipitate until Q is equal to KSP. And that gives, and so now we're going to look at problem number 62 on the in-class assignment. So problem number 62. Oh, I didn't mean to go there. Hit the wrong tab button. Okay, so will cobalt hydroxide, and that's cobalt-2 hydroxide, precipitate from a solution if the pH of a 0.020 molar solution of cobalt nitrate is adjusted to pH of 8.5? So first thing first is I'm going to write out the equilibrium reaction for it right above here. So cobalt hydroxide, cobalt-2 hydroxide to be specific. It does dissociate to some extent to give us cobalt-2 ion plus 2 hydroxide ions. So cobalt-2 hydroxide, and so there is that. We can write out the equilibrium constant expression, KSP, is equal to the concentration of cobalt-2 times the concentration of hydroxide ion squared. All right, and we need to look at our our KSP table. So Appendix D. So I'm going to go back over here and then tab, and we'll look at cobalt. So 1.3 times 10 to the negative 15. And I'll go ahead and write that down. 1.3 times 10 to the negative 15. Okay, so there is our KSP and our value and our expression. Now on this, we're not going to need to do a concentration table because we already have the concentration of the cobalt, and so here our concentration of cobalt is equal to 0.020 molar. All right, since our pH is 8.5, that means that our pOH is 14 minus 8.5. So we'll do 14 minus 8.5, and that gives us 5.5. Well, I'm just going to leave that as 5.5. Our concentration of hydroxide is going to be this, 10 to the negative 5.5. Normally, if we were doing a problem, I would evaluate that. I'd punch that in the calculator and get our concentration of hydroxide. But what that means is we can just take this and we'll say Q is equal to our concentration of cobalt, which is 0.020, times 10 to the negative 5.5. And since it's squared, we're going to call that a square. And you'll see right away, if you do 10 to the negative 5.5 squared, that's going to be 10 to the negative 11. And then times this, it'll be 2 times 10 to the negative 13. But we will, let's go ahead and punch that in. So let's do 10 to the negative 5.5 is that number. But then we're going to square that quantity. And we get 1 times 10 to the negative 11. And then we're going to multiply that by 0.020, and that gives us a Q value that is equal to 2 times 10 to the negative 13. So 2 times 10 to the negative 13. So now we want to compare Q to K. Well, K was 1.3 times negative 15. 10 to the negative 13 is greater, so Q is greater than KSP. So therefore, yes, a precipitate will form. And that is how you play the game, will a precipitate form. As I mentioned, perfect for your holiday get-togethers, 4th of July celebration, Christmas, whatever, Thanksgiving. This would be a great birthday parties. Okay, I maybe am overselling this. I don't think maybe you want to do this at a birthday party or at Thanksgiving, unless you just have that particular kind of family. So let's look at this next one. In this one, we've got silver iodate, and we want to know, will silver iodate precipitate? So let's go ahead and write out the equilibrium reaction. So we've got silver iodate solid. So will it precipitate? Let's go ahead and write this as silver ion plus the iodate ion. So there is the iodate ion. And now we got the silver ion and the iodate ion. And let's see. KSP is given to us, and we'll write out the expression: concentration of silver times the concentration of the iodate, which is equal to 3.1 times 10 to the negative 8. So there is our KSP value. So to do this problem, we need to do the dilution equation twice, because here we've got 100 milliliters of this silver ion solution and 10 milliliters of this, so we're diluting both of them. So we are diluting both of them. So the dilution equation is M1V1 is equal to M2V2, and so M2 is M1V1 over V2. So M1V1 over V2. And now what we want to do is solve each of these. So our concentration of silver ion, which is equal to M2, is equal to M1V1 over V2. Our original concentration of silver ion was this, 0.0100 molar. Our volume was 100 milliliters. And volume 2 is 100 plus 10. So I'll put 100 milliliters plus 10 milliliters. All right. So we'll punch that into our calculator. So 0.0100 times 100. And then we will divide that by 110. And that gives us 9.09 times 10 to the negative 3 molar. And that's our concentration of the silver ion. For iodate ion, the calculation is quite similar. So M1V1 over V2. We'll have different values for M1 and V1. M1 for the iodate is going to be 0.0150, so 0.0150 molar, 10.0 milliliters, and then 100.0 milliliters plus 10.0 milliliters. And we will calculate that value. So 0.0150 times 10. And we'll divide that by 110. And we get 1.36 times 10 to the negative 3 molar. Well, now we just need to calculate Q by putting both of those numbers into the expression. So Q is equal to 9.09 times 10 to the negative 3 and 1.36 times 10 to the negative 3. So times 9.09 times 10 to the negative 3. And the number we come up there, 1.24 times 10 to the negative 5. Now we just need to compare that Q to K. So Q is greater than KSP. So yes, a precipitate will form. So yes, a precipitate will form. And so that's the end of our in-class assignment problems. There's one more page that I want to show, which is kind of interesting, and it is in section 17.7. And it is about qualitative analysis. In the lab, we do this qualitative analysis experiment. With that experiment, when we add, on that one we've got silver ion, we've got nickel, we've got iron, and chromium. And so we can separate those out by looking at small differences in the solubility between certain categories of ions. We'll find that some ions will precipitate when we put them with chloride. And those ones include silver, lead, mercury, copper 1 will do this as well. So if we add HCl, we can precipitate those, but then the remaining liquid, after we centrifuge, the remaining liquid will contain everything else. So we can go further on and analyze these using different tricks. So we can take the remaining things and add, let's see, H2S and some hydrochloric acid, and that will form these sulfides. So these are sulfides that are insoluble in acid. And we'll get this. And then we can make the pH basic and do sulfides that are insoluble. Let's see, acid insoluble. Well, yeah, so these are the acid insoluble. The most sulfides will be insoluble in base. But we can take the rest and increase the pH, and we will get hydroxides. And we'll also get some of the acid or base insoluble sulfides here. And then we can separate those out and do some other things. So by knowing these KSP values, you can set it up so that you can do qualitative experiments based on quantitative information. So this is just sort of the basis for that particular lab, which is why I like to show this page. All right, well, the next page on this chapter 17 is this, my favorite page in every chapter.